an application of what we did last time, which is the fundamental theorem of calculus. So, as an application, we will see integration by parts, which is also a very important result. And we will see, of course, in R the very basic variant of it. Okay. Okay, so let us put as theorem, integration by parts. I think notes are already uploaded, so we can see this notes as well. So suppose f and g are two continuous functions on closed interval AB and continuous on closed interval AB and differentiable on open interval AB. I assume f prime and g prime are both Riemann integrable. On interval AB, then integration a to b fx dx fx g prime x dx is equal to ft gb minus fa ga minus integration a to b f prime x gx dx. All right, you have seen this one. Yeah, the formula you have seen because you have done integration by parts several times with the usual function. So your differentiability was already there, continuity, differentiability both are already there, and you know Riemann integrable also. So you have not seen perhaps in the underlined assumption which are used for this formula. So let us see a proof of it. The proof uses the fundamental theorem of calculus. Tool use the fundamental theorem of calculus. All right. How do you use? Consider the following function. Consider hx to be defined as fx times gx on closed interval AB. Right. Now, what are the properties one has? H is continuous on AB, and since product of differentiable function is differentiable, H is differentiable on the open interval AB. All right. Now, what about integrability? Since f and g both are integrable, h is also integrable, Riemann integrable. On AB. So by the way, let me ask you a question. So what about integration in open interval or integration in closed interval? Does that matter? Endpoints?
It shouldn't matter.
Yeah, I could not hear. Say that again.
So I said I don't think it should matter.
Yeah, so this is a confusion you'll see most school student has, right? Sometimes in open interval or in closed interval. Suppose function is defined on open interval, not in closed interval. Can you say function is closed interval, integrable on the closed interval also? A function is integrable. It doesn't matter because the finite number of point of discontinuity doesn't matter, right? So endpoints one can consider as discontinuities once the function is bounded. So as soon as function is bounded, it doesn't matter. Is this clear? Yeah, and I said here H is Riemann integrable. Why is that so? Can anybody tell me why is this H Riemann integrable? This is because H is continuous on AB. All right. Now consider H prime X, which is Fx G prime X plus F prime X Gx. Product for all X may be open. Now the point is here is an exercise to check. So uh, f g prime. So this is an exercise. Check f g prime is Riemann integral. So in general, product of a continuous function with a Riemann integrable function is Riemann integral. So we show this one. Okay. So once this is Riemann integrable, then what you get is we'll just integrate a to b h prime x dx, which is nothing but integration a to b f fx g prime x dx plus integration a to b f prime x gx dx. But what is this by fundamental theorem of calculus? This is equal to h of b minus h of a. This by fundamental theorem of calculus. Right? Now, what is this? HB is FB, GB, minus FA GA. So that gives us, this implies integration A to B fx g prime x dx is equal to fb gb minus fa ga minus integration A to B f prime x dx dx. All right. So this actually gives the proof of the integration by parts. So this actually is the proof. Now the point is, here you see, I mean, this can be generalized in you will see this later. This can be generalized very much. So suppose this is A and this is B. So if a function vanishes at the endpoints, then you see both of them are vanishes. So if suppose the function is, one function is like that, sorry, like bump function, right? So bump function is useful in the in case of integration as well, right? So suppose this is phi, and you want to find integration f p prime, f p prime a to b. So then if you use integration by parts, you will have this one, right? fb times pb. So here dx, this is fb by integration by parts, integration by parts. fb pb minus fa pa minus integration a to b f prime p dx. All right. So this part will then vanish because this phi is 0. So one can think of this as real axis. So phi of b equal to phi of a equal to 0, just like kata function. So one have actually minus a to b a prime phi dx. Now the point is, suppose, so this is a nice result when f and phi both are differentiable. But now this becomes a definition derivative when f is not differentiable. So a sense of differentiation can be made. So even if f is not differentiable, one can make sense of derivative in certain sense, not usually the classical sense, in certain sense, by the following equation. So this is integration a to b f prime p dx, by definition minus a to b f p prime dx for all p such that so phi belongs to a certain class of function. Yeah. So open interval. So it means phi, this means phi has compact support. So that's it. So this means x in AB such that phi x is non-zero this closure is compact. So this cis infinity is the set of all function free such that this one differentiable function such that this. So this actually becomes a definition later on. So that's we'll not go further beyond this one, but this is very important once you go into the theory of partial differential equations, for example, where in classical sense you will not find solution. So this is called so F is called distribution. So this is much more general. So the funda is basically the integration by parts, and using fundamental and integration by parts is proved by using fundamental theorem of calculus, and then you have this. Any question here? Any question? Okay. Change of variable. So here I'll just state it and in the exercise to prove, because we have done several things using partitions. So this will be the proof will be used. Partition will be used in the proof. So suppose phi from CD to AB be a continuous, strictly increasing function such that
Sir, so the previous point you made about making sense of a derivative. So this
yeah,
basically tells us that a function which is only continuous almost everywhere we can still reconstruct some sort of a derivative for it.
exactly, yeah. So that will be used in. I mean, you will see in functional analysis those who are going for mathematics. In measure theory function analysis, that you can remove the set of measure zero set, and still if it is function is defined there, it is absolutely fine. You can do a lot of stuff, and there later on after those courses you will see that one can make sense of derivative even if the function is not defined in a measure set of measure zero. Yeah.
Oh, okay, sir.
Okay. So suppose phi be a continuous strictly increasing function such that phi is differentiable on open interval CD, assume phi prime is Riemann integral on AB, then integration A to B fx dx equal to integration C to D f compose phi y, phi prime y dy. So this is the usual rule, usual change of variable what you do for doing integration, for evaluating integrations. And yeah, the proof uses lower sum upper sum argument. So you look at lower sum upper sum in this sense here for this one, and so this which will be equal to, well, you use this one uh, lower sum upper sum argument here also. Well, you since it is increasing, so you get the partition in terms of phi, and then use the mean value theorem, we'll get it. Using mean value theorem, you get it. All right. So this proof is an exercise. You find in definitely in the books, but I'll suggest that you do this one so that you become comfortable with upper similarity argument. The next thing is a very important one, which is interchanging limit and the integration. So which means you have a sequence of functions. So the question is, suppose Fn is a sequence of functions. Uh, so whether limit n tends to infinity integration sequence of the sequence of integrable function, Riemann integrable function. So Fn x on AB. The question is whether we have this one. All right. So whether you can change this integral sign with the limit. Right. So this is a question. Right. What do you think? Is it possible to interchange? Yeah, so you have seen sequence of functions in the very beginning because I want you to get comfortable with sequence of functions because it will be keep on coming up again and again. And you see in every chapter, this sequence of functions is coming back. So the question of limit, interchanging limit and integration, so that part you will be able to appreciate once you know sequence of functions very well, and that is the reason why I have taken that difficult topic in the very beginning. Otherwise, yeah.
Maybe if it converges uniformly, we can say this.
So uniform is a very strong condition, yes. So that is what we are going to prove. So this will be important. Yeah, but what about point-wise? Yeah, point-wise doesn't give much things, right? So let's look at, so suppose Fn converges to a point-wise on AB, then the above interchange is not always true. So let us look at a couple of examples. So one is actually our known examples. So example one. So this one, remember we have defined this function. Fnx is limit m tends to infinity cos factorial n pi x whole to the power 2m. Do you remember? X belongs to, let's say, 0, 1. Do you remember that function? This function?
Yes.
Yeah, so Fn converges to Fn converges to F, which is where?
N is an integer.
Pointwise, where fx is what? Yeah,
Fx is 0 at
zero where x is irrational, right?
Hmm.
And 1 when x is rational. Yeah. So you can
Yes.
see that f is not, we know that f is not Riemann integrable, right? So the question remains to show whether Fn is Riemann integrable on 0, 1. Yeah, what do you think? Is it Riemann integrable, Fn? So yeah, the point is, how do you know a function is Riemann integrable? How do you think?
The region sum converges.
No, first thing is you need to see whether the function is continuous.
Yes.
If it is continuous, it is Riemann integrable. You know that. If not continuous, you need to look at the point of discontinuities and see where how many points you have where point of discontinuities are there, where discontinuities are there, right? So you
Yes.
see here, when there is this factorial becomes n factorial x becomes an integer only when there is this discontinuity, right? So if n is discontinuous, at the points where factorial nx belongs to Z, right? Which means the set of discontinuities of Fn is equal to the set x in 0, 1, x, let's say x equal to, x has to be rational. If it is not rational, it cannot do. Let's say, maybe I should write q such that this q is less than n, less than equal to n, right? It should cancel with factorial n, right? Q should cancel with factorial n, so q must be less than equal to, right? This not just in q intersection 0, 1. Is this clear? So we are looking at 0, 1 closed interval. 0, 1 closed interval. The set of continuous function on 0, 1 is this set, right? Is it clear? This can become integer when x is rational. Only when x is rational. And not just all rationals, if the rational is of the form p by q, then q must be less or equal to n. If the rational is in the reduced form, where P and Q are co-prime, then Q must be less or equal to N. Is this clear?
Yes, sir.
So how many points are there?
Countably infinite.
Yeah, so finite limit, right?
Yeah. Sorry, yeah.
Right. So this the discontinuities, set of discontinuities of Fn in 0, 1 is a finite set. Hence, Fn is Riemann integrable on 0, 1, right? So this is how one would look. This is Riemann integrable. So each Fn, what we get is each Fn is Riemann integrable on AB, but F, which is limit Fn, is not. All right. So we get a function sequence of functions which is Riemann integral, but in the limit, pointwise limit is actually not Riemann integral.
So why is the pointwise limit not Riemann integrable? It's discontinuous on a countably infinite set, right?
No, discontinuous everywhere, right? You know,
Uh,
it's a Dirichlet function.
okay.
Yeah. So this is what our standard example, which uh, which was not Riemann integrable. Even it was in front of Riemann as well. Riemann said it's a bizarre function. So yeah, so it comes as a limit of Riemann integrable function. So pointwise limit can be very, very bizarre. All right, let's look at another example. Okay, so next example would be there you get functions, the limit functions to be integrable, but it may not be the same. Integration may not be the same. So consider Fn x to be nx 1 minus x squared to the power n on 0, 1. So what is the limit of this sequence? Pointwise limit? Yeah. This is an exercise in for sequence in sequence of series of not just function, it's sequence of real number. Limit, fix an x and you want to find n tends to infinity f n x. So that is equal to 0. So it will be of the form something like n to the power alpha by 1 plus p to the power n, where p is greater than 0, in this form. So it should be along the same lines as this. Here you get this one as positive, so this is less than 1, which you can write 1 over and make it 1 plus something. Yeah. So it is of the same form like that. So you have to go through along the same lines. All right. Now let's see what is this integrable. So this is Fn are continuous. Fn is a continuous function on 0, 1. Hence it is Riemann integrable. So therefore, you find 0 to 1 fnx dx. It is not very tough. So it is x1 minus x squared. Sometimes calculation is important. Dx, so which is nothing but n by 2, 1 minus, there is a minus, x squared to the power n plus 1 by n plus 1, restricted to 0 to 1. So which means at 1 it is 0, so at 0 minus sign goes away, n by 2 times n plus 1, that remains. So limit n tends to infinity, integration 0 to 1 fnx dx is limit n tends to infinity n by 2 times n plus 1. What is the limit here?
1/2.
1 by 2, right? So and integration fx dx, so which is, what is f? So this is fx. Let me find this. So f is the limit fx dx, which is integration at 0 to 1, 0 to 1, limit of fnx dx, right? So this is 0, which is not equal to half. So therefore, and you see this, you see this does not converge uniformly. So these examples says that for pointwise convergence, limit and integration cannot be interchange. All right. However, we can interchange the limit and the integration provided the convergence is uniform. The theorem is called uniform convergence theorem. The theorem is called uniform convergence theorem. So UCT in short. So you'll see some other CTU will be coming up. Convergence theorem will be coming up in the third year if somebody is going for maths. So this is the very basic one. Uniform convergence is a strong convergence. So there are a lot of nice things happens in uniform convergence. Okay, let's look at the statement. Let Fn be a sequence of functions on a sequence of Riemann integrable functions on AB such that Fn converges to F uniformly on AB. So we assumed uniform convergence. Then F is also Riemann integrable on AB and integration a to b fx dx is limit of integration a to b fnx dx. So now we can interchange the limit and the integration. All right, is the statement clear? We just need uniform convergence. Then the limit will become Riemann integrable provided the sequence is Riemann integrable, and how to evaluate integration, that is also there is a limit, interchanging limit and integration. All right, is this fine? The statement. So this is one of the very important theorem in this course. So I mean, these things will be keep on coming up, and don't get confused. For pointwise convergence, integration limit cannot be changed. Differential limit cannot be changed. For uniform convergence, integration goes very well. You can change limit and integration. For differentiation, there is a problem. We need extra steps of the derivative, uniform convergence of the derivative. All right? Is this clear? Yeah, not clear. Okay, anyway, so let's go into the proof of it. So statement is much more important than the proof here. So maybe I should put as remark the statement of this theorem is much more important than its proof. So I'm giving the proof for the record. It's very simple, not difficult at all. But proof is not that important. Statement is very important. So it is important to understand the statement and you try to apply few situations. So for the proof that since it converges uniformly, so we look at this fnx minus fx modulus and take supremum of this on AB and call this as epsilon n. Right, n belongs to natural number. So this epsilon n is a sequence of real number. So you see clearly fnx minus fx is bounded by minus epsilon n to epsilon n. Now this gives you that fx is bounded by fn x plus epsilon n and fn x minus epsilon n. All right? Yeah, is this fine? Now we take integration. So not just integration, you look at upper sum and then go to the upper integral. And it is monotonic, so we have upper and lower both. So here we go lower integral fn x minus epsilon n dx. It's lesser equal to lower integral a to b fx dx. So we don't know whether this is integrable or not. So this part is here it is integrable. So here we have this lower integral is always upper integral fx dx. And this upper integral, if you go that side in terms of upper integral, we'll see a to b fn x plus epsilon n dx. Right. Now, since fn fn minus epsilon and fn plus epsilon is Riemann integrable, we have so this lower integral will become integration fn x minus epsilon n dx lesser equal to the lower integral fx dx lesser equal to the upper integral fx dx lesser equal to integration a to b. Upper integration becomes an integration because it is integrable fn x plus epsilon n dx. All right. Now we look at the difference between this difference between this lower integral and this upper integral, right? So a to b upper integral of x dx minus a to b lower integral of x dx, right? So if you look at this sign, so this should be greater or equal to 0 because upper integral is always bigger, and this side is lesser equal to integration of this one, so which means a to b fn x plus epsilon n dx minus this one, right? Integration a to b fn x minus epsilon n. What happens? Epsilon n dx. So which is this side is nothing but you see 2 epsilon n integration a to b dx, which is epsilon n times b minus a, right? Since fn converges to f uniformly, epsilon n goes to 0 as n tends to infinity. Therefore, from 1, you obtain that this mod of a to b upper fx dx minus integration a to b lower fx dx is equal to 0. Right? You take take n tends to infinity, and this side, right side, goes to 0. This implies it to be upper fx dx. So we can write this one as less than equal to epsilon and strictly less than. This one, b minus a, which goes to 0. Same tends to infinity. So this upper integral is equal to b fx dx. The lower integral. This means f is integrable. Right? So we get a to be f to be integrable. Right? Is it clear? See, there is nothing much. One just need you need to use the inequalities. Two inequalities, nothing else. Right? So we proved that f is Riemann integrable. What is remaining is this part. So let's see how do we prove the interchange of limit and integration. All right. Now again we will use this step. We'll use this step, right? So maybe call this star. We now rewrite star as so these are f is Riemann integrable, so this becomes equal. So integration a to b fn x minus epsilon n dx is less or equal to integration a to b fx dx less or equal to integration a to b fn x plus epsilon n dx. All right. Now from here you look at look integration, you just subtract by integration fn x dx each of the terms. So what we get is minus epsilon n integration a to b dx is less or equal to integration a to b fx minus fn x. Well, we write it differently. A to b fn x dx less or equal to epsilon n integration a to b dx. So this implies minus epsilon n times b minus a is less or equal to integration a to b fx dx minus a to b fn x dx less or equal to epsilon n times b minus a. So this means what? As n tends to infinity, this modulus will be less than any epsilon. So this means limit n tends to infinity integration a to b fn x dx is a to b fx dx. Is this clear? Yeah.
Yes, sir.
Yeah, so the proof is actually not very difficult. This is the statement is important. So we'll show next time few examples, couple of examples applying this result maybe, and then we'll go into improper integral, where you can allow the limit, one limit to be infinity, and then evaluate the integral. All right. Any question? So about showing answer straight, actually, what I find after looking at some copies, that some people might not want to see they see the answer script. So I'll upload by tomorrow morning the marks in WeLearn, and those who want to see the copies will send me an email, and then I will reply back with the answer script maybe, and then in the evening we'll discuss. Okay. So tomorrow evening we'll have discussion, but by morning I'll be able to upload the marks. So first four question was very easy. So most of the people will not be able to. I mean, will not need to check the copies. Any question? Okay, then we'll see you next week.